The problem of sorting is to take a list of objects, rearrange them so that they are in some order, such as the common one of from smallest to largest when we talk about a list of numbers. Remember, this list of numbers could just be the keys. Again, we don't worry about the content associated to the keys, just focus on the keys. The content is somehow moved when the keys got moved. There are many ways to sort. Indeed, in the past, we used sorting as a way to understand complexity, because sorting is about counting the number of comparisons, just like what we did for the searching problem. There are many interesting techniques to talk about sorting. For this video, we show 2 sorting methods and leave the rest in our recitation and tutorials and more in other courses. Besides complexity, one other important thing here is about correctness of what we do. That is, how do we know that what we did can always give what we wanted, which is a sorted list. We will talk about this in details in our review. Let's develop our first sorting method through sorting playing cards. Given the cards as shown, how do we sort it? You need to pretend you are a computer program that can see only a limited number of cards at a time. Usually we mean you can see 2 cards and not all of them at a time to then compare and sort them. We can imagine the given cards in the unsorted part and we want all of them put into the sorted part at the end. The obvious way is to go through cards in the unsorted part, find the smallest card not in hand and put it at the end of the sorted. Repeat doing it until there are no more cards in the unsorted part. Note that at any moment we can work with 2 cards at a time, compare the 2 cards to do something with them. This is good enough for our purpose to go through whatever in the unsorted part to find the smallest so far. At the beginning, we have the very first card to be the smallest so far. Then we looped to see the next card, which is the king, to compare with the current 6. 6 is still smaller than king. We keep 6 and move on. Same for 7, we move on. 10, we move on. Now 2 is smaller than 6. 2 become the smallest so far. Now A, it's not smaller than 2, we move on. King is not smaller, we move on. But now we are at the end of all the cards. We have found 2 to be the smallest card not in hand. We now move 2 into our sorted part. Then 2 is gone. Then we repeat going through all the cards, started with 6 and found that 6 is indeed the next smallest. So 6 is here and 6 is gone. Next, we repeat starting with king and at the end of it, we found that 7 is the smallest and 7 is gone. Then we repeat for the remaining cards, which are king, 10, ace and king, and 10 is found to be the next smallest card, and so on. We are done with all the cards now, and we have the list sorted in the sorted part. This method of going through unsorted part to get the next smallest one to put into the sorted part is actually what we call selection sort. Here is the Python code. We define the function selection sort, wanting to sort A, the list. We define the sorted as an empty list, unsorted to be a copy of the input so that we do not destroy the input. Then we go through the unsorted list, which originally is the input A, until it is empty. We take the smallest so far as the very first one in the unsorted list. Then we use a for loop to look through it to get the smallest among all the unsorted guy and assign it to be the smallest. At the end of the loop, we can remove the smallest from the unsorted list and add it to the sorted part. Once this while loop is finished, when unsorted is empty, we will return the sorted, which is the list of sorted elements in the input A. What are the time and space complexity then? We talk about 3 possibilities: average, best, and worst. Average means on the average over all possible inputs of A, how much time we need. Best means for some input A, we use the least amount of work for the algorithm. And for worst, for some input A, what can cost the most amount of work for the algorithm. For our selection sort code, we always use n squared amount of time, where n is the number of input elements in the list A. This is because we always run through the nested looping, the outer while, and the init for. So it's n times n, therefore n squared. As for space, we actually use an extra data structure called sorted. We have n elements in the sorted list. For selection sort, actually, if you are allowed to destroy the input A, you may be able to reuse a space and do not need to pay a linear space. I shall leave that to you to try it out. Let's try another method. Remember when we talked about searching, we used the partitioning strategy. Let's see how it applies to here. Here is the idea. Split the cards into two halves and wishful thinking each is sorted, then combine halves into one sorted list. We run through the example here. There are 7 cards here. We split into two halves. The left has 3 cards and the right with 4 cards. For the 3 cards on the left, we use our wishful thinking that they are supposed to be sorted. For that, we actually go into a recursion to solve it. So it is partitioned into 1 card, 6, and 2 other cards, king and 7. And 6 itself as a card is sorted. King and 7 has to be again recursively solved, and they are divided into a king and a 7. Both are individual cards, so they are sorted. And then they are merged easily by doing a comparison into 7 and king, and then the 7 and king merge with the 6 into 6, 7 king to be a sorted list of 3 cards. Likewise, on the right, we have 4 cards. They are now divided into 2, 2, and the 2 here, 10 and 2, are now divided into 1, 1, and they are sorted then. With that, we can merge them into 2, 10. Similarly, for ace and king, they are divided again, and the ace and the king are now merged into king and ace. Now we have 2 pairs of cards sorted, and these 2 and these 2 are then to be merged. We shall skip the merging here to then see a bigger one later on. So the 4 cards are now merged. At this point, we have 3 cards sorted and 4 cards sorted. We now see how they are actually merged. We have one part 2, 10, king, ace, another part 6, 7, king. So these 2 lists are merged by looking at their head. In this case, 2 and 6, and 2 is smaller than 6, so it is outputted into the result. Then 6 with 10, 6 is smaller. 7 with 10, 7 is smaller. 10 with king, 10 is smaller. King of spade versus king of diamond. King of diamond is smaller. King of spade versus ace. King is smaller. Then A has no one to compare with. A is simply appended to the list. And we are done. This approach is called merge sort. The name is quite representative of the action. Merging is the main effort here to get the list sorted. It is a recursive algorithm as we saw. Base case is when n is 1, that is only one item, and it is sorted by itself, so we can return the list. If not a single item, we have 2 or more items, and we can divide it into 2 halves, recursively sort each of them, then merge them. Here is how the code looks like. Define, merge, sort the list that we want to sort. If the length is less than 2, means there is only one item, then we can return the list. Otherwise, we divide the list into the left half and the right half and recursively sort each half. The list on the left is from the first item until before the middle guy, and the list on the right is from the middle guy until the end. After the left and the right part have been sorted, we merge them into one sorted list. The actual actions are now in the merge function. Here is the merge of the left and the right. The result of the merge is initialized to be an empty list, while the left and the right are non-empty. If the first item on the left is smaller than the first item on the right, we take the left item to be part of the results and we remove it from the left. Otherwise, we take the right to be in the results and remove it from the right. At the end of the while loop, the left or the right could be non-empty. In that case, we take all the remaining in left into the results. We also do the same for the right, and we return the results. What is the time complexity for our merge sort? Same as what we saw in searching. We had size of n, then half n, and so on until 1. So there are log n levels of recursion. At each level, we spend O(n) time for the merging. So it is O of n times O of log n to give n log n. And there are no difference for all the best, average, and worst case. As for space, we need on space as we need an extra list to hold the merge results. We are now done with two example sorting methods. There are two characterizations we want to highlight about sorting. First, in-place sort. It is an algorithm that needs only O1 extra space to complete sorting. Extra space here means space that outside of the input list. So such an algorithm does not need space that is proportional to the input length of the list to be sorted. Our Python code for selection sort in this video needs the extra space to keep the results. On the other hand, as mentioned, we could have done it without extra space, but to reuse the input list. In this case, we need to alter the input list. As for merge sort, it's hard to do so, though it's possible. Second, stability. Stable sorting algorithms maintain the relative order of records with equal key values. That is to say that when we have the same value or key at different positions in the list, at the end of the sorting, the same value records should maintain their relative positions. Remember, we often sort keys with associated records in real life. So two keys have the same value can have different associated records. We often do not want to disturb their relative positioning because there could be some sorting already done to the records. You will see the use of this characterization in our face-to-face lessons. Our selection sort implementation is stable, but if we want to also have an in-place selection sort, then it is likely to be not stable. Our merge sort in the video is not in place. We keep an extra list for the result, and it is easy to enforce stability. We are reaching the end of this lecture. Let's mention the built-in sorting in Python. List.sort. The method sorts the list in place and is stable. It has two parameters here, key default to none, reverse default to none. Key specify a function of one argument that is used to extract a comparison key from each list element. Reverse is a boolean value. Is set to true, then the lists are sorted as if each comparison were reversed. This method modifies the sequence in place and returns none. Note that Python has a separate function, sorted, that you can use to sort a list without modifying the list and return a new list. Let's see some examples. A is a list of numbers. If we do a.sort, then it simply takes the numbers and sort it in increasing order. We have 1, 2, 3 and so on. This is the same as if you take A, you sort it with taking the key as the value itself and the reverse order is false. Next, we show a case where you can change the key to be the remainder of 5. In this case, you take the value x, find its remainder and then do the sorting based on the remainder. The remainder of 1 is 1. The remainder of 2 is 2. Remainder of 7 divided by 5 is 2. So it comes here. And 32 is also remainder of 2, 3 remainder of 3, 313 remainder of 3, 4 is remainder of 4, and 34 is remainder of 4. Also notice that this order respects the stable order. 2 is before 7, so 7 is after 2 as after sorting. And likewise, 3 is before 313, both with remainders of 3, so 3 then 313. This sorting by Python is stable. Here is just a simple example of reverse sorting. Given the list of number, if you reverse sort it, you will get the reverse order. The largest come first and the smallest go last. For sorting records, each record usually has a key and other info that we need to move together with its key when doing sorting. Let's see some examples. Here we have students record, students with the name, the grade, and a score for 5 students. When we do students.sort, the default key is the index 0. That means we sort by the names of the students. So Ben B come first, followed by Dave D, then J for Jane, and then J for John, and last Simon with S. If we do sort the key to be the index 2, which means the grade here, 15, 10, 8, 21, 12. And if we do it reverse order, that means the largest come first, then the smallest. Largest is 21, then 15, then 12, 10, and 8. So Simon 21, John 15, Dave 12, Jane 10, and so on. We're now at the end of the lecture. We study in this lecture Python lists as mutable data structures. We study searching. We show a linear search, an obvious way of searching, and then a better way of searching if the list is sorted with divide and conquer strategy. We study sorting. We show a straightforward sorting, selection sort, and we use the same strategy as divide and conquer for binary search to do merge sort with recursion. And we mention two characterizations of sorting, in place and stability. We show the built-in list.sort method. Do note that there is another function called sorted that doesn't change the input